Given for us here is the graph of the sine curve. We're going to use that graph to find the derivative of the sine curve's graph. So how do we do that? We begin by looking at the SIGN sine chart for the graph of the SINE sine function. So we'll draw a number line, and below the number line I'll write theta to indicate that I'm looking at the values along the theta axis, and above it I'll write y prime to indicate that I want the SIGN of the derivative. Two key things happen on the interval between 0 and 2 pi. One of them happens at pi over 2. That key thing is you have a horizontal tangent line to the curve of the SINE. Where you have a horizontal tangent line, the derivative is 0 because the slope of a horizontal line is 0. We do this again at 3 pi over 2. We have a horizontal tangent line. The slope of a horizontal line is 0. Slope, the derivative are the same, so we have 0 there. Now, let's look at those three separate regions for this graph. From 0 to pi over 2, the graph of sine, S-I-N-E, rises. And if it is rising, any place that you draw a tangent line, you're going to have a positive slope. Positive slope means positive derivative. That happens again from 3 pi over 2, and in this graph up to 2 pi, the graph rises along from 3 pi over 2 to 2 pi. If it rises and you draw tangent lines anywhere along there, that slope is going to be positive, and that tells me the derivative is positive. Now let's look at the interval between pi over 2 and 3 pi over 2. Looking at the graph of the sine curve, we see that it is falling. If you were to draw a tangent line anywhere along that curve, the slope of that tangent line would be negative, so the SIGN of the derivative is also negative. We are going to use that SIGN chart to get the graph of the derivative of the sine function. What will that look like? Where the SIGN is positive, the graph of the derivative is going to be above the x-axis. Where the SIGN is negative, the graph of that derivative will be below the x-axis, and again where the SIGN is positive, the graph of the derivative would be above the x-axis. What you see now is that the graph of the derivative of sine of x gives us the graph of the cosine x function, one of your derivative properties. The derivative with respect to theta, sine theta, is cosine theta. Example, if f of x equals x times sine x, find the second derivative of x. To do this, we're going to begin by finding the first derivative. Notice that you have x times sine x, so that's a product rule. And the product rule for y equals the product of the first function times the second. The derivative is the derivative of the first times the second plus first times the derivative of the second function. Let's find the first derivative. F prime of x is equal to the derivative of the first function x is 1 times the second function is sine x plus the first function is x, and the derivative of the second function sine x is cosine x. The first derivative, f prime of x, is sine x plus x cosine x. Now we're ready to find the second derivative. The second derivative, f double prime of x is equal to the derivative of sine is cosine x. Now, to find the derivative of x times cosine x, we're going to need to use the product rule. Again, in using the product rule, we'll have the derivative of the first function, the derivative of x is 1, times cosine x, plus, then we have the first function x, times the derivative of cosine, which is minus sine x. This simplifies to cosine x plus cosine x minus x times sine of x. So, the second derivative, f double prime of x, is equal to 2 cosine x minus x times sine x. Now tangent x and secant x. Because we know the derivatives of the sine and cosine function, we can derive the derivative of the tangent function. Let's begin with a trig identity. d dx of tan x is equal to d dx of the trig identity sine x over cosine x. In order to find the derivative of one function divided by another, we need to use the quotient rule, which states if y is a quotient of the high function divided by the low function, then the derivative is equal to low d high minus high d low divided by low squared. Let's apply this rule. We begin, and I'll write the cosine x squared first, and we'll have the low function, which is cosine x, times the derivative of sine x, which is cosine x, minus the high function, which is sine x, and then the derivative of cosine is minus sine x. Continuing, cosine x times cosine x is cosine squared x, minus sine x times minus sine x is plus sine squared x, and that is still divided by cosine x quantity squared. The trig identity, cosine squared x plus sine squared x equals 1, and you have 1 divided by the cosine squared x. 1 over cosine is equal to secant, so 1 over cosine squared x is equal to secant squared x. We have another trig property, and that is the derivative with respect to x, tangent x, is secant squared x. Memorize this. d dx of secant x. We'll use the trig identity that secant is 1 over cosine of x. Now we have a quotient, so we'll use the quotient rule again. The quotient rule states if y is equal to the ratio of the high function divided by the low function, then the derivative is equal to, don't forget that the L is squared in the denominator, low d high minus high d low. Let's apply that rule. This will be equal to, the denominator is cosine x quantity squared, and then we do the low, so it's cosine x times the derivative of 1. The derivative of 1 is 0 because 1 is a constant, minus high is the number 1 times the derivative of cosine, which is minus sine x. That would be equal to cosine times 0 is 0, and in the numerator you've got a negative times a negative, so that's going to be a positive sine x, and in the denominator we have cosine x, that's cosine x squared. Let's do a little more trig. That can be written as sine x divided by cosine x times 1 divided by cosine x. Sine x over cosine x is tangent x, and 1 over cosine x will give us secant x. So the derivative with respect to x, secant x, is equal to tan x secant x. Make sure that you memorize this as well. You should verify that the derivative with respect to x of cotan x is equal to negative cosecant squared x, and the derivative with respect to x of cosecant x is equal to negative cosecant x cotan x. Example, find the tangent line to the graph of y equals tan x secant x at x equals pi over 4. In order to get the equation of a line, you need 3 pieces of information. You need a point on the line, you need a slope at that point on the line, and you need an equation of the line form. Let's begin by finding the point. The point will be the ordered pair, pi over 4, and the function evaluated at pi over 4. So let's evaluate y at pi over 4. That'll be the tangent of pi over 4 times the secant of pi over 4. The tangent of pi over 4 is 1, and the secant of pi over 4 is the square root of 2. The product of 1 times the square root of 2 is the square root of 2. Now we need the slope. The slope we obtain by finding the derivative first and then evaluating the derivative at the desired x value, which is pi over 4. Notice that with the derivative we have first times second, so in order to find the derivative we need to find the derivative of the first times the second plus the first function times the derivative of the second. Y prime is equal to the derivative of the tangent we just learned is secant squared x. The second function is secant x. Then we write the first function, which is tangent x, and the derivative of secant x we just learned is secant x tangent x. Continuing, secant squared x times secant x gives us secant cubed x, and then we have a tangent x times secant x times tangent x, which would be tangent squared x times secant x. That's the derivative. Now we need to compute the slope, which means we're going to evaluate this derivative at pi over 4. That'll be the secant of pi over 4, and then we will cube that, plus the tangent of pi over 4, square that, and the secant of pi over 4. The secant of pi over 4 is the square root of 2. We cube that. The tangent of pi over 4 is 1. Square that. And the secant of pi over 4 is the square root of 2. square root of 2 cubed will give us 2 times the square root of 2. Then we still have plus the square root of 2. So 2 times the square root of 2 plus the square root of 2 is 3 times the square root of 2. So the slope is 3 times the square root of 2. Now we are ready to get the equation of the line. To get the equation of the line, I'm going to use the point slope form. Y minus y1 equals m times x minus x1. Let's put in the values. It'll be y minus the y1, which is the square root of 2, is equal to the slope, which is 3 times the square root of 2, times x minus pi over 4. Solving for y, you get y is equal to 3 times the square root of 2x. We distribute that 3 times the square root of 2, so now you have 3 times the square root of 2 pi over 4, and then add the square root of 2 from the left-hand side to both sides, so you got plus the square root of 2. That's our equation of the line. Example, find f prime of theta if f of theta is equal to cosecant squared theta divided by theta. Let's go ahead and rewrite that cosecant squared theta as the product of cosecant theta times cosecant theta divided by theta. We have a product rule, so that's how we get around powers. We still have a quotient here. So to find the derivative of a quotient where y is equal to a high function divided by a low function, the derivative y prime is equal to the low squared, and the numerator is low, d high for the derivative of the high, minus high, d low for the derivative of the low. F prime of theta is equal to, let's begin by writing theta squared in the denominator. Then we're going to have theta, that's the high, times the derivative with respect to theta of the numerator, which is cosecant theta times cosecant theta, minus, we have the cosecant theta squared times the derivative of the bottom. Theta is going to just be 1. Continuing, f prime of theta is equal to theta times, and we need to take the derivative of the product cosecant theta times cosecant theta. To do this, we have the first function multiplied to the second. The derivative would be the derivative of the first times the second plus the first times the derivative of the second. The derivative of cosecant theta is minus cosecant theta, cotangent theta. Then we multiply it to the second function, which is just the cosecant theta. Continuing, then we have plus the first function is cosecant theta. Then we need to take the derivative of the second function, which is cosecant theta. So that's minus cosecant theta, cotan theta, and we still have minus the cosecant squared theta. This becomes theta times. We have two of these terms, so you have minus because of the negative and the negative, 2 cosecant squared theta cotangent theta minus the remaining cosecant squared theta, all divided by theta squared. And if you wanted to, you can factor out the common cosecant squared. We get that f prime of theta is equal to negative cosecant squared theta times 2 theta cotan theta plus 1, and don't forget the denominator of theta squared. Example, applying special limits. The 2 special limits that will be used in this example set are the limit as x approaches 0 of sine of x divided by x equals 1, and the other special limit is the limit as x approaches 0 of 1 minus cosine x divided by x equals 0. Let's do part A. Find the limit as x approaches 0 of the sine of 4x divided by x. We want the limit as x approaches 0 of the sine of 4x divided by x. We need to do some creative arithmetic. The first thing I'd like to do is multiply by a factor of 1 that is written as 4 divided by 4. Rearranging a little bit without changing the value, I'll have the limit as x approaches 0 of 4 times the sine of 4x divided by 4x. Now we can use the first special limit property on the sine of 4x divided by 4x. We would write this as 4 times the limit as x approaches 0 of sine of 4x divided by 4x, and the limit as x approaches 0 of the sine of 4x divided by 4x is exactly the limit as x approaches 0 of sine of x over x. Therefore, the limit is equal to 4 times 1, which is equal to 4. The limit as x approaches 0 of sine of 4x over x is equal to 4. Part B. Find the limit as x approaches 0 of sine of 3x divided by the sine of 7x. That is the limit as x approaches 0 of the sine of 3x divided by the sine of 7x. Let's rewrite this so that it looks like the limit as x approaches 0 of sine of 3x divided by 1 times 1 divided by the sine of 7x. Remember, what we're trying to do is rearrange and manipulate the numbers and signs so that we get to use the special limit property, the limit as x approaches 0 of sine x over x equals 1. Looking, we need an x over x, that's a factor of 1. We also need a 3 over 3, that's a factor of 1. And 7 divided by 7, that's another factor of 1. And we will reorder these terms to make it fit. So this will give me the limit as x approaches 0 of sine of 3x, and I will regroup the 3x and write it below the sine of 3x times the sine of 7x is in the denominator, and I will regroup the x and the 7 from the numerator and write that in the numerator, so I have 7x divided by sine of 7x. And what is now remaining is we have an unaccounted for 3 and a 7. Let's write this out. This would be moving the constant outside of the limit 3/7 times the limit as x approaches 0 of the sine of 3x over 3x times 7x divided by the sine of 7x, which will give you the 3/7 stays put. Sine of 3x over 3x as limit approaches 0 is 1. Same thing for 7x divided by the sine of 7x. So our limit is 3/7. Find the limit as x approaches 0 of sine of 2x times 1 minus cosine x divided by x squared. Let's expand this a little bit and write this as the limit as x approaches 0 of the sine of 2x divided by x times 1 minus cosine x divided by x. Let's multiply by a factor of 1. So I'll multiply the top and bottom by 2. This will give me the limit as x approaches 0 of 2 times the sine of 2x divided by 2x times the limit as x approaches 0 of 1 minus cosine x divided by x. This special limit is equal to 0. So you'd have 2 times the 1 times 0, which is equal to 0. The limit as x approaches 0 of sine of 2x times 1 minus cosine x divided by x squared equals 0.